Welcome back from the spring break, those of you who seem to have made it back. 3 important announcements. The midterm is March 24th, that's a week from Thursday. It's only going to cover 3 topics. Prediction, that means regression and classification. Concentration measure and minimax theory, nothing else will be on the test. I put up some practice problems. And rather than spending a lot of time going through a review and solving them on the board, I thought it would be better just to actually post solutions. So Jisoo is kind enough to make up some solutions. We can talk about them the day before the test if you want to. But they're also posted on the web page. So if you go through your homeworks and these practice problems and you're comfortable with that, then you are in perfect shape for the midterm. All right. Any other questions? Any questions at all about the midterm? Yeah, Mike.
Are there solutions for homework 2 and homework 3 going to be posted?
Well, they should have been, but
I mean, they might be, but I'm pretty sure they're not.
you're probably right. So I'm going to make a note to yell at Jisoo. Sorry, Jisoo. I thought I put them up. So 2 and 3?
Yeah.
Okay, let me check. I actually thought
3 were still working, so it makes sense.
Yeah, 3 definitely, but 2 I thought I'd definitely put up, but maybe I didn't. So I shouldn't blame Jisoo just yet. Any other questions? All right. Also, somebody pointed out to me that according to the university schedule, there's no class April 14th. I checked that, and it's true. I guess it's carnival or something like that. So apparently no class April 14th. All right. So where are we? So we're about to start unsupervised learning, which basically means you're not predicting anything. You're not predicting any Y's from X's. You just have some data, and you're doing stuff with it. And these are 2 long topics coming up. The first one is clustering, and the next one after that is graphical models. And so we're starting with clustering. Both of the notes are up there. So they're both large topics because there's a lot of methods out there. So let's talk a little bit about what clustering is and then how we're going to solve it, or at least we'll look at some of the solutions. Well, what is clustering? So clustering is kind of one of those things that intuitively we all know what it is. It just means finding clusters in the data, as the name implies. But it's hard to pin down. So I have these 2 little examples on page 2. If I gave you some data that look like this, and I said, are there clusters in the data? I think without having formally defined what we mean, we'd say, yes, there are 2 clusters, this one and this one, right? I think sort of whatever clusters mean, those are clusters. Then it becomes a little bit less clear when I look at figure 2, I put down, this is all one data set. Okay, how many are there clusters there? I'd say yes. How many clusters would you say are there? Three or 4, yeah. So depends what you mean by a cluster, right? So you could say that's a cluster, this is a cluster, this is a cluster, this is a cluster. Or you might want to say this is just one cluster and it's kind of split up. So you can see it starts to get kind of vague and hard to define. So I think a lot of the literature on clustering is confusing because people will often present clustering methods without even defining what they mean by a cluster. So I think it's really important, if we're going to make progress, that we have some well-defined notion of cluster. And so in this class, I'm going to define, for the most part, a specific version of clustering. I'm not saying it's the only definition or the best definition, but at least it's a definition and it's a clear thing, which is namely going to be high density areas. So if I draw a density, let's just do a one-dimensional density. Say it looks like this. In some sense, I think what we usually mean by clusters, at least when we're thinking of having data drawn from a distribution, is that there's some population quantity we're actually trying to estimate. And it's the high density regions of the distribution. So what do I mean by a high density region? One possibility would be to cut across the density like this and say which regions are above that cutoff, so that would be here, here, and here. And that might be one possible definition of what you mean by clusters. And you could say any clustering algorithm, the way we should judge how well it's working is how well is it estimating those sets. Okay? Now, there's a couple problems with that, which is, what if I draw the line somewhere else? So there's two ways to deal with that problem. One method, well, there's more than two ways, but two common ways to deal with it is we could look at all the clusters as I vary this cutoff. That will actually produce a tree, something called a cluster tree. A second way of doing it is if I draw this again, you might notice there's another natural way to define high density regions, which would be to cut right here and here, and call this one high density region, one region, and one region. And what we're doing there is we're sort of using the modes, in some sense, of the density to define what we mean by the clusters. So these are two slightly different ways of talking about what we mean by using the density function to define clusters. One looks at these upper level sets, and one looks at some partition based on the modes. And they're very similar, but they're not exactly the same. And we will talk about other definitions of clusters, but for the most part, when we start off with, this is how we're going to think about clustering. Okay? Any questions? And most of you have heard of k-means clustering, which doesn't seem to have anything to do with this, right? So we'll talk about k-means clustering shortly. But I think starting with density clustering is better because it's got a very, very clear, intuitive target that we're trying to estimate. So in fact, I'm going to start with this method. So what we're going to do is somehow find the modes of the density and then use the modes to split the sample space into a partition. And so this is called mode clustering. This is an interesting thing about mode clustering, or mode-based clustering, is that in computer vision, it's been the basis of clustering for many, many years. And yet, in machine learning and statistics, it's much less common to talk about clusters this way. It's not unheard of, but it's just much less common. I'm not sure the history of why in computer vision it became so popular much earlier, but it seems to have a longer history there. And we're going to talk about a specific algorithm for finding these mode-based clusters called the mean shift algorithm. Has anyone heard of the mean shift algorithm? Well, you either haven't or you don't want to put your hands up. No, okay. Anyway, I'll explain what it is. But let's start with that. So, okay. So again, the goal is I have an underlying unknown density function. I have a sample from it. I'm going to think about these modes. I'm going to assume there exists some finite set of modes. So we'll make an assumption like that. But how do I actually divide the space into regions based on those modes? Well, in this one-dimensional case, it seemed pretty clear. Between this is a local maximum, this is a local maximum. Somewhere in between has to be a local minimum. And similarly here. But when we get to a high-dimensional space, even a two-dimensional space, suppose I have a density lying above the blackboard here. And there's a mode here, and a mode here, and a mode here. Now I have to ask myself, where does this point belong? Does it belong to this mode, or to this mode? It's not so obvious anymore how to divide up the space. So how do we take our intuition from one dimension and go to two and higher dimensions? Well, one way to do it is as follows. If you look at what I'm really doing here, why is it that I said, let's say this point here, why is it that I said this point belongs into this partition? Well, if you look at the density there, and imagine now following the density like following the highest ascent path. Think of it as doing gradient ascent if you're used to doing optimization. If I keep moving, every time, imagine taking a step in the direction where the density is higher, you're going to go all the way up to here, right? And this will be any point to the left of this line is going to, wherever you start, if you climb the density, you're going to end up at this mode. Okay, and the same is true if I look in this region that I've carved up here, pick any point in here, let's say this one, and follow the same algorithm. Just climb the density, go up, you will end up at this mode. And similarly for this one. So one way to characterize what I've drawn here is to say if we follow the gradient ascent path, or the climbing up the density, that divides the whole sample space into the basins of attraction of these different modes. Okay, and we can try to do the same thing now in higher dimensions, but maybe we should try to, first of all, formalize what that means in an equation. What I'm really saying is I'm defining a path. So let's take again a point here, x, and I'm imagining again climbing the density. So what does that mean? It means as I climb the density, this point is following some sort of path until I get to this mode. So you can think of there's a path, x of t. Let's think of t as time. And as time evolves, this point is moving and it gets to some sort of mode. But how do I characterize that? How do I define what that path is? Well, what's happening in general is the path. So we can think of a path starting at x. What is a path? A path is just a mapping, which is taking, we'll think of it as time. So it's taking r and mapping it into, in this case, it's mapping it into R1. But in this case, if I imagine starting at a point here and following the density, this path is going to be some curve in R2. So in general, it's going to be an RD, whatever the dimension of the space is. So this is the path at time 0. So actually, pi x at time 0 is x. It starts at x. And then again, I want to think of it as moving up the density. And what that means is really the following differential equation. If I take the derivative of that path at time t, it should be the same then as I want to follow the maximum of the gradient. So it should be the same as taking the gradient along that direction. It should be the gradient of the density at that time. Let me just pause and make sure that that's clear. That if you picture a density function up here, and if I want to go uphill, that means I have to follow the derivative, right? So I have to take the gradient of the derivative. At that point, let's say this is a point at time t. The gradient of the density is pointing in some direction. I want to make sure my path is following that direction. So the derivative of the path should equal that thing. Or in other words, if you remember your calculus, this is just the integral curve. Remember, in calculus, you define things called integral curves. This is the integral curve starting at the point x. Actually, this is ending up at a mode m. And so technically, it's this differential equation. But if you prefer, just think of it as, in our drawing there, as just climbing up, just taking a little step each time. You look and say, you're climbing a mountain. You look around, where is the steepest step I could take? You take that step and you keep going. That's the intuition. But this is just saying exactly the same thing. And so under certain fairly weak conditions, this differential equation with this starting condition defines a well-defined path, and you can show that it must go to a mode. Okay, so there's some mild conditions here, but subject to these conditions, every point x, if you solve this equation, you get a path. Pi of x indexed by time, it climbs to a mode. So that's called the destination of the path. The destination starting at x is just the limit of the path as time goes to infinity. It's infinitesimally small. Think about taking a small step size and taking the limit. That's why we get a derivative. In practice, we're not going to do that, but yeah.
I have some confusion here. So you are actually dividing the anti-mode.
Well, the boundaries happen to be the anti-modes, yes.
So you need to do descent instead of ascent.
No, I'm talking about this point here, okay, so I think it'll be clear when I keep going, because I haven't defined the boundaries yet. I'm just telling you if I start at a particular point x, there's going to be some mode I'm going to end up. I haven't defined the partition yet. I'm just saying given any starting point x, there's some, it goes to, let's call this mode 1, mode 2, mode 3. If I picked a different starting point, say here, it might have this destination. And if I pick this point here, it might go like this or something like this.
Which local maximum?
No, for any starting point x, it's going to go to one of the local maxima. Right? You pick any x and follow its path. And again, just picture like a mixture of normals and climbing up, higher and higher. You start at any x, it's going to climb to one of the modes. Does that make sense? Now you can show the following, that these things do not overlap. They actually partition the space, all these paths, except in the sense that if I started earlier here, I'd go here. If I start later on the path, I end up on the same path. But if I have two paths, in other words, are either one is part of another path or they're disjoint, except at the modes. They're going to line up at the modes. They form a partition of the space. Okay, but now I can say the following. For a given mode, I can ask which points are attracted to that mode. Now I'm going to define the clusters. Those are called the basins of attractions or the clusters. There's lots of names for them. What did I call them? I think I called them some A sub j. So now let's suppose I have, again, some finite set of modes. Let's say mode 1, mode 2, mode 3, mode k in this space. For every point x, it's going to go to one of these things. So I can define A sub j to be the set of all points x whose destination is mode j. That's what I've drawn up there for you, are these clusters or basins of attractions. In other words, it's going to look like this. Okay, and what this partition means is every point in here goes to this mode. Every point in here goes to this mode. Every point in here goes in this mode. So I literally, if I took the density and you had some software that would figure out what this path is, it's basically running gradient ascent on that density, you would discover everything in here goes to this mode, everything here goes to this mode, and so on. In our simple one-dimensional case, this is mode 1, this is mode 2, this is mode 3, and then the basin of attraction is A1, A2, and A3. These things all belong to this mode. These all belong to this mode. These belong to this mode. If you want, you can think of it as turning the density upside down and letting water run and asking where would the water go? Which mode would it go to? Think of it as helium, so it goes up. In fact, this is also called a flow for exactly that reason. Okay. So roughly speaking, it's just, you have these modes, and then you have all the things that flow to the modes, and that defines the basins of attraction, as they're called, or in our language, we would just call them the population clusters. This has nothing to do with data right at this point. This is just something about the distribution itself, the true density function. Okay. And there's a nice picture here on page 3, the top. I put a density with 4 bumps in it there, and you can see, then I drew a picture of it. You can see the 4 modes, and I actually figured out numerically where the basins of attraction of those 4 modes are. And so you can see there that those 4 modes define 4 sets. Okay, everybody with me? Any questions? How do I know the boundary is smooth? So how the boundary behaves is, there's a whole branch of mathematics called Morse theory, which is part of differential topology, which characterizes how all these things behave. In fact, these are, under certain conditions, These boundaries are themselves submanifolds. And there's some little bit of detail here that I haven't told you about saddle points, points that have derivative 0, but they're not maximum, they're not minima. They live on these boundaries. And in fact, the flow on these boundaries goes to these saddle points. But these are sets of measure 0, so statistically they're not very important. Let me draw a simpler example of that. Suppose I have a maximum here and a maximum here. And then there's some sort of boundary in between them. So a point here flows here, and a point here flows here. But if I started right on the boundary between, where would the flow go? It turns out there's going to be some critical point on here, and everything on this thing flows to this critical point. Okay, but that's not so important for us because statistically this is a set of measure 0. We're just really concerned about the maxima. What happens exactly on the boundary for us is not so critical. So just to summarize, because I don't want it to get too complicated, we're just going to find the modes and then find for each point, we're going to see which mode it belongs to. That's all it is. The idea is quite simple, actually. Any other questions? All right. Now comes the good news, because we can do this with data too, right? If we really had to, do some analysis to solve this differential equation, it would all be hopeless. We don't know what the density P is. So the good news is there's a very simple way to actually implement this in practice. Let me find a brush here. All right. So step 1 is going to be, since I'm using the density as the basis for doing my clustering, the first step is going to be density estimation. I'm going to estimate the density. So we're going to do a density estimator. Now, in principle, there's many density estimators, but for doing this task, it really is best to use a kernel density estimator because it leads to a very simple algorithm. So, in fact, let me remind you, the kernel density estimator with bandwidth h looks like this. It's 1 over n okay, and we're going to use the Gaussian kernel, which turns out also to be computationally very convenient for this problem. So K is just a Gaussian. This is just a standard kernel density estimator with bandwidth h. Okay. Good. So far, so good. Now, whoops, where is this? Okay, here we go. Now, we have our estimator, but we have 2 tasks we need to deal with, which is how do I find the modes of this thing? That's not so obvious, right? Maybe in 1 dimension, you could just take a grid of points and look at the density and find the modes. But what are you going to do in higher dimensions, in 2, 3 dimensions or higher? How do you find a mode? And then I have to find these gradient descent paths. For every point in the space, I want to know which mode does it go to. Well, that's what the mean shift algorithm does. So here's the algorithm. It's extremely simple. Now, I should say too, let me draw another picture here. So we're going to try to find the modes, but I want to know for every point in the space which mode does it go to, but usually we just care about the data points. So we're going to also have some points, and we want to know for each point which mode does it belong to. Does it go here or here? Now this grid of points that we're going to look at could be an arbitrary grid of points, but it's usually the data points. But just to keep it general, you'll see in the algorithm box on page 4, I allowed it to be some arbitrary set of points. A1, A2 up to AN. Okay, again, in practice, this is usually the data set. But I want to distinguish the data from the grid. The grid are the set of points that I want to know. I want to know which cluster does this belong to, which cluster does this belong to, which cluster does this belong to. And in principle, it could be any set of points that could be asking about. But again, in practice, this is usually going to be identical to the data. But conceptually, it's better to keep them distinct. And so how do I answer this question? it turns out there's a very simple algorithm. And it looks like this. We pick one of these starting points. I'll say A1. And now we iterate it. So we take A1. And what we do, let me just first of all draw a picture of what we're doing. What we're going to do is this. Say this is your starting point. I'm simply going to take the average of all the other points. But I'm going to take a kernel-weighted average. So I'm going to put a kernel above this. And so I'm going to give high weight to things near here and low weight to things further away. It's a lot like nonparametric regression, in other words. That's going to give me a new point. And now I'm going to repeat that exercise. I'm going to take this point. I'm going to take a kernel-weighted average of the points. And that'll be my next point. So the iteration looks like this. At the step, let's say step s plus 1, you just take a kernel-weighted average of all the data. Let's just say this is the jth guy here. A sub j minus. This is the last iteration of this algorithm. That's why I have s and s plus 1. Normalized by the kernel. So if you just look at that, it's just what I said. I take, say I'm at step, I'm looking at the jth point. I'm going to repeat this for every point in the grid. So I'm at the jth point, a sub j. I'm worrying about this point. I'm iterating this algorithm, so I'm taking s equal to 0, 1, 2, and so on. And I take the current point. And again, all I'm doing is taking the xi's averaged, but I'm centering a kernel at the current point. And that gives me a new average, and it's going to move, and I'm going to repeat until it doesn't move much. And there'll be some stopping criteria when it doesn't move much anymore, for example. Is that clear?
So is the mode of the kernel always, is the kernel always unimodal? And is the
It's not unimodal, or we wouldn't be finding any clusters.
No, a kernel function.
Oh, well, I'm using a Gaussian kernel here.
So is that, so you can't use any general kernel?
You can use the general kernel. The algorithm's going to change a little bit. Yeah. The algorithm just has a very simple form when it's Gaussian kernel.
Wait, so where does p hat comes into this?
Well, let me, so right now I haven't explained the connection. That's a good question. Let me just make sure the algorithm's clear. So now I take every one of these points. I run this some number of times until I think it's converged. And I do this for each point. What I'm getting out, I'm claiming. Let me show you. Actually, I'm going to show you what you get out. Look at page 4, figure 5 at the bottom is a typical example. So what you see there is I had a bunch of data points here and a bunch of data points here. And I ran this, I don't know, 10 times. And what you see is that these all flow. I plotted the flows here. These all flow here. And I've solved both problems at once. I found the modes, and I know for each data point which mode it belongs to. So the whole clustering problem is now solved.
So the xi's were drawn from P originally?
The xi's are a sample from some underlying density P, right? Now, so a couple of things. First of all, there's a reason why I really wanted to separate the query points A from the data, because even though these might be data points, we're not changing the data points as we move along. As I move this query point, the original data that define the kernel are still staying the same. No, this is still xi, in other words. To answer the question, what has this got to do with the original density estimator? Maybe we'll do this as a homework, I don't know. But it can be shown that this is nothing other than doing a gradient descent algorithm. Since we don't do optimization in this class, I probably won't do it. But when Ryan taught this class, I think, or helped me teach this class, and we had a section on optimization, I think this was a homework problem, which is very easy to show that if I just gave you a Gaussian kernel density estimator, a kernel density estimator with a Gaussian, and said, do gradient descent but with a particular schedule for changing the step size. So that, in other words, I give you any point and I say just do the gradient descent path, you would get out this algorithm. This is just gradient descent with a particular adaptive step size. That's the connection with the... So if we didn't have a Gaussian kernel, the iteration would look a little bit different. You can do other kernels, but the most common one is the Gaussian. See this, notice that x times k, what does that look like? It looks like the derivative of a Gaussian. So if it's not a Gaussian, it's okay. You can do this for other distributions, but let's just assume it's Gaussian kernel.
So in the figure where you describe the algorithm, you say the input is p hat, but so the idea is that we just take the estimate derivative in place of the...
Well, the input is p hat is that's a bit loose. What I meant was you don't actually have to, actually I shouldn't have said that at all because you don't ever input p hat. You just compute these iterations. So yeah, I don't know why I said input p hat. I mean, conceptually you're inputting p hat, but when you program it, you're not actually inputting p hat. So I want to make sure is the algorithm clear? And you're going to get exactly something like this. Any questions?
So does the number of points in A has to be the same as the number of data points?
No. The number of points can be any. The points in this thing can be anything. This is going to tell you for each point what mode does this belong to. It's just that usually in practice, what points do we care about? Well, it's usually the data points you want to cluster. So usually it's taken to be the data points. Yeah. But I've seen people just take a grid covering the space and ask for each grid point, where does it go to? You can do that if you want to. It's slow, but if you want to do that, you can do that. Okay. Let me see if there's any other questions. All right, so the nice thing about this is, first of all, you can see programming this is really, really easy, right? That's as simple as it gets. And I think conceptually it's pretty simple. We're just finding the modes and finding, which points go to which modes. So it's got a very nice interpretation. It's very simple to implement and so on. There is one tuning parameter, which is the bandwidth. Frankly, though, I think that's much easier than most clustering algorithms where you have to choose the number of clusters as a tuning parameter. That's a much harder thing, in my opinion, to choose. But you still do have to choose this tuning parameter. We'll talk more about that in a minute. Now, before I go on, let me make a few other comments about this algorithm, which is this is the basic mean shift algorithm. And this goes back to, when was it first proposed? Maybe in 1985, I'm going to say. And of course, since then, there's been a whole industry of people working on this algorithm. And so there are many speeded up versions of this. Because it's actually not a fast algorithm in the computational sense. It's a fast algorithm in the human sense. It's easy to program. But computationally, what happens is the following. It's actually instructive to plot the paths out. Because what you'll see is, suppose I have data like this. Suppose I have a data point here. What you'll see is very quickly this moves up like this, like in one step, 2 steps. But then as it starts to get close to this mode, it starts to follow the first local principal component, and it starts to go really slowly. So there are lots and lots of methods out there. You can look up mean shift fast, and you'll see there are lots of fast methods that speed up the convergence, and there's all kinds of interesting numerical stuff that I'm not going to talk about, but there are ways to make this algorithm much more efficient. So the algorithm I'm talking about is sort of the original simple version of mean shift clustering.
So you said you think it's easier to pick a bandwidth than the number of clusters?
Yeah.
Isn't that going to be the same problem in this case?
Well, we'll come back to that, but say you're doing k-means clustering, the problem of how do you pick k is, as far as I know, an unsolved problem. Whereas picking bandwidths, we have lots of ways to do that.
Am I right that the number of clusters is going to depend on the bandwidth?
Oh, yes, you're right. Once I pick the bandwidth, the number of clusters will be determined by the algorithm. Absolutely. Yeah. And it's not that picking a bandwidth is necessarily easy. I just think it's easier than choosing the number of clusters in some other algorithms.
Is that acceleration the same as the acceleration gradient descent?
I don't know. I don't know enough about optimization to tell you what the fancy versions of the algorithms do, honestly. It's probably something like accelerated gradient ascent, but honestly, I just don't know. And there's many versions of these speeded up algorithms. It also depends on how accurate you want things to be. From my point of view, I don't know. I run it 10 times and declare victory. It usually works pretty good. Although we had a visitor once, I'm blanking on his name. He's actually very well known for his work in mean shift clustering. He's from Spain, and I'm sorry, I'm blanking on his name. And I said, I run it 20 times and I declare victory. And he says, 20 times? Oh my God, I would never want to run something 20 times. I have millions of pixels to deal with in an image. I just want to run it 3 times and get convergence. So what you call fast depends very much, I guess, on the domain you're working in and the size of the problems you're dealing with.
When you say how many times you're running, you're talking about how many iterations?
Iterations.
Not restarts, because that is deterministic, right?
Iterations, right. That's right. Yeah. All right. So I also wanted, here's some more pictures, just some fun pictures.
I'm sorry.
Yeah.
Real quick. So in practice, after you've done some number of iterations, how do you actually group the...
You have to set some sort of threshold, and let's say 0.0001, and any 2 points that are within 0.00 you declare to be the same cluster, some basic threshold. In principle, if you could run it forever, they would literally be the same point, right? But that's usually pretty easy to tell. So if you look at this example on page 5, I tried to pick some really examples that were known to be tough clustering examples, and I just ran my own mean shift code, probably very inefficient code. Top left is the data point. I don't know how well this actually came out. The top right, I wanted to show you that even after a few steps of mean shift, this is just like 3 or 4 steps, it's already almost clustered. And then what the bottom left shows is something called blurred mean shift. That's one of the speeded up versions. I won't go into the details, but I was just trying to show you that it converges a bit faster. I'm not sure how well that's actually showing up. But you can see the same thing in the bottom plot, that there's the data. I did a bit of mean shift, and I did one of these speeded up versions, and I don't know how well it shows up, but again, there are methods that converge faster. Somehow it looked better on my screen, but I'm not sure you can see the difference that well here. All right, so there is one problem, which is how do we pick the bandwidth? And there's a variety of ways you can do this. One answer, in fact, one thing they do in computer vision is they don't pick a bandwidth. They try lots of bandwidths and they look at what you get out. Although that can not always be such an easy thing to do, especially in a high dimensional problem. Now let's get back to your question though about how does the number of modes relate to the bandwidth? Here's a very special property about Gaussians. Suppose you're doing one-dimensional density estimation. Do you think if I make the bandwidth smaller, that the number of modes increases? Or at least is non-decreasing? So if I were to plot, this is, say, the bandwidth, and this is the number of modes, you might expect this, right? That the number of modes should get bigger as h gets smaller. And the answer is that's if and only if the kernel is Gaussian. It's a very interesting result. The Gaussian is the unique kernel which has this property, which is one of the reasons why people like to use Gaussian kernels in this setting. However, it's not necessarily true in higher dimensions. So this is particular to one dimension. But still, we have to pick a bandwidth. And here, there's lots of different ways you can pick a bandwidth. One of them is in 705, did we talk about cross-validation for choosing bandwidths? Yeah. So the most common way people would use is just use cross-validation, the standard method for picking the bandwidth.
Doing that, even if we were using the Gaussian kernel on the high-dimensional case, this is not the case with this kind of graph.
That's right. This could go up and then down and then up again. in high dimensions. Yeah, I think it's not well understood, actually. It's related to the problem of, if I take, just as an aside, if I take a mixture of k Gaussians, how many modes are there? The answer is nobody knows. It's not k. You can come up with examples where it's less than k, but you can also come up with examples where it's much more than k. Turns out that the differential topological behavior of even a mixture of Gaussians is a very complicated question. It's pretty much an unsolved problem. Not much is known about it. And so this is obviously very related. That the exact behavior of the number of modes as a function of h is not that well understood theoretically. Of course, we always can compute it and see how many there are, so it doesn't really affect us in practice. But theoretically, it's not that well understood. So method one is to do cross-validation. There are other methods you can do. Some people use what's called Silverman's rule of thumb, which is nothing other than a bandwidth which is known to oversmooth a little bit, which might be a good idea when you're clustering. Question?
So we're using cross-validation because we're looking for a stable number of modes?
No, you're just trying to minimize the cross-validation error.
What?
Oh, did we not? So this is a question. Did we do? I thought we did cross-validation for density estimation.
Oh, for density estimation?
Yes.
So I think the equation implies a loss function for
L2.
Okay, so this is just the density.
Right. That's right. So we estimate this and minimize h, which is not necessarily saying you're choosing a good bandwidth for finding modes, but it's just a simple way to pick a bandwidth. Another common method is to do this. Let me explain what this is. This is a kind of overall standard deviation. This is just the standard deviation, or the sample variance of the jth feature. And this is just an average of that. So it's some overall standard deviation, or variance. And now you take the bandwidth to be that over n to the 1 over 4 plus d. This is the optimal rate for the bandwidth for kernel density estimation. And this is just a scaling to make sure it's on the right scale. So if you're in kilometers or miles or centimeters, you want to have it on the right scale. And in fact, this is actually pretty much the optimal bandwidth if it was a very smooth density. In practice, what people find is that this method tends to oversmooth. But oversmoothing and clustering is not such a bad idea. You're probably more interested in finding big clusters, not little wiggly clusters. So if you do a little bit of extra smoothing, that's probably not such a bad idea in clustering anyway. So this is another popular choice for the bandwidth. Yeah. What does oversmoothing mean? Well, if this is the true density, and if this is my estimated...
So it's getting the number of modes with the true density?
Oversmoothing just means smoothing more than the optimal mean squared error.
Okay, so all of this really just has to do with the density estimator.
That's correct.
You can't evaluate the clustering.
We can. We'll get to methods that deal directly with that shortly. Yeah. This is right now, you're right. We're just talking about trying to pick a good bandwidth for the density estimator. There's another approach which says, when you think about what we're really doing, we're doing gradient descent. We don't really care about the density. We care about the shape of the density, which is what? It's the gradient of the density. Maybe we should try to pick a bandwidth that's optimal for estimating not the density, but the gradient. And you can do that too with cross-validation. I don't think it's important enough for the class that we should go through it, but for your information, I've included it in here. It's on page 6. You can look at it if you want. It's just cross-validation, but instead of trying to estimate this risk, we try to estimate the risk of the derivative. And it just involves a small change in cross-validation. Okay, and in general, by the way, just for your information, the rate of the optimal bandwidth I've always written like this. That's the, in kernel density estimation, we always found that was the optimal bandwidth. If you're trying to estimate the derivatives, the optimal bandwidth actually looks like this, where r is the number of derivatives. So for the gradient, r would be 1, there'd be an extra 2 there. For the second derivative, r would be 2, and so on. So all of the rates that we're used to would actually have an extra term if we were talking about derivatives of functions instead of functions. It's kind of an interesting side note, but not critical for us. It's there if you want to see it. Yeah, I probably put too much information about that, but anyway. That's the main challenge in mean shift clustering, I think, is though finding a bandwidth that you like. And then there's the speed issue, which, as I said, it's not a fast algorithm in the computer science sense. For me, it's fast. I consider it fast. But if you're going to do millions of data points, you probably do want to look at one of those speeded up versions. Okay, so that's method 1. I want to talk a little bit about the theoretical properties of this method. Before I do, let me just see any questions about how you would actually implement this. Okay. So the nice thing about it, again, is it's very simple, and I think it's pretty clear what it's doing. Now, I'll just tell you something about the accuracy here. I'm on page 7. So, which has a theorem about how accurate is this method in the sense of how accurately are we estimating these modes. And what this theorem says, let me explain what this means. So I'm saying, the theorem says, suppose that P is a density with modes, say a finite number of modes, and you'll notice there's an extra term there. It says that P is a Morse function. So a Morse function just means that at each critical point, at each point where the gradient is 0, you have to assume that the Hessian is non-degenerate. Okay, that's what a Morse function is. And most of the theory that's derived for this type of clustering has to assume that the function is a Morse function. It's not a very strong assumption. It just sort of rules out weird flat spots and things like that where you wouldn't have a well-defined mode. So it's basically saying, that this mode has like a well-defined negative curvature at the mode. That's what a Morse function is. And what ends up happening is, if I look at, I'll just write it like this. What can be shown is that with probability tending to 1, and if h does not go to 0 too fast, then the estimated density will also have k modes. So the true density has k modes, and the estimated density with probability tending will have k modes. And the estimated modes with high probability have distance something of order h squared and something of order this really should look familiar. It looks very much like the usual bias variance trade-off, except for one thing. So this should be familiar. This is like our bias term. This would look like our variance term if it didn't have the d plus 2. But modes converge at a slightly different rate than the function itself, because it involves the gradient, basically. Now, if we look at this, this might be a discouraging result, because d is here. That says there's a curse of dimensionality. But I'll tell you something about clustering in general, which is that we don't necessarily have to let h go to 0. This gets to your question about, are we trying to estimate the density or find the modes? That really you can get away with keeping it, using an h that doesn't go to 0 as n goes to infinity, because if I use a fixed bandwidth here instead of letting it go to 0, what's going to happen? There will be some bias. Well, I didn't draw that too well, but there's going to be some bias. But so what? In terms of the clusters that we find, they're going to be very similar, right? What we care about in clustering really isn't the L2 error. It's stating the shape of the density in the resulting clusters. So in fact, letting h go to 0 is not necessarily a good thing to do when you're clustering. And if you don't let h go to 0, if you keep it, let's say, bigger than some small fixed constant, then this behaves like a constant. And we're saying we don't care about the bias. And so this actually converges at a very fast rate. So I'm just saying that the theoretical result looks a little bit more discouraging than what you're actually going to see happening in practice. That this tends to often work very well in multivariate problems, even though we might not be estimating the density well. It's very much like classification. Remember we saw that in classification, you could estimate the regression function poorly and still get a good classifier? It's pretty much the same phenomenon. You could estimate the density poorly in the L2 sense, but you're still finding basically the right clusters. So a similar phenomenon happens. OK, and if you want, I put part of the proof in there.
Does it mean that L2 is actually not suitable?
That's right. For clustering, to be honest, the usual loss functions like L2 are not the right loss function. The problem is trying to make it all right is kind of complicated. I think there are better loss functions to use, but I just didn't think we would go there in the class. Because it starts to get into something called topological data analysis, which one of our students knows a lot about, which is about getting shapes of things correct. But it's a long diversion that's probably not worth it for the class. All right, now, so that's good. We've made good progress here. We now have a way of doing clustering with a well-defined population target. It's based on the density. We have an algorithm that's very simple that we can implement. There's some theory for it and so on. But that's not the only way to extract clusters from the density, as I hinted at earlier, which we can see if we draw some pictures here. Suppose the data looked like one of those things I drew earlier. So we have to think about what's going to happen if I run my favorite clustering algorithm. Well, first of all, for those of you who know k-means, you can see k-means is not going to work so good on an example like this. What happens if I run this mode clustering? Well, what it's trying to do, if you think about what the density looks like, is it's kind of like a low density out here. Then there's this high density region that's kind of like a ring. And it's going to be, if I actually plot the density estimate, it's going to be some fluctuation along this ridge. There'll be like a ridge here, but with some fluctuations on it. So you might end up randomly with a mode here, and a mode here, and a mode here. And probably these guys will all flow here, and this will all flow here, and this will all flow here, and this will flow here, and this will flow here. So you'll probably get something looking like that. Now, is that good or bad? Well, if you could do some sort of post-processing which says, look, we have a cluster here and a cluster here, but they're pretty close together, you could imagine maybe merging some of these very close clusters, we could recover this ring. And in fact, there are ways of doing that.
So we're supposed to be imagining that the density is kind of like about equal over the circle?
Yeah. Yeah.
So it doesn't really have the Morse.
That's exactly right. Yeah. Okay. But there's another way to recover the information, which is to look just at the high density regions. This is something I mentioned earlier, which is it's kind of hard to picture here. But imagine cutting across the density here. You would get a nice ring. And as you cut down low and lower, you're going to get a thicker and thicker ring. Let's draw it in. Since I can't draw in high dimensions, again, I'll draw the the lower dimensional version. What we're going to do is, for every real number t, I'm going to form what's called the upper level set, which is simply, okay, so that's just the set of, let me write it out actually more clearly than that. L sub t is the set of all x such that p of x is bigger than t. So in this picture, it's this, and this, and this. And in this case, the level sets would be things that look like this. So in some sense, this is maybe a better summary than just the modes of what the high density regions look like. And notice what's happening here is that I can always break this level set into its connected components. See, there's 3 connected components here. So I called that, I wrote it like this, that the level set we can write as a union of, let's say C, J equals 1. The number of connected components could vary with T. So what I'm doing is I'm collecting together all of the connected components. Well, here they are, C1, C2, C3. But now what I can do, so did I give that a name? Yeah, I'm going to call C sub T this collection of sets. So in this case, it's C1, C2, up to CKT. But now let's move this T. I can do this for every possible T. And what I get then is this, the collection of all clusters, of all level set clusters. Let me just draw another picture and make sure it's clear. Okay, so for this T, there's a single connected component, and this is it. For this T, you can see there's 2 sets. For this T, there's 1 big set, and so on. Those are my clusters. I'm going to call them all clusters, and I'm going to take the union, and that's what script C is. That's the set of all the density clusters. Is that clear? And rather than finding a mode or picking a particular level, maybe we should try to summarize this entire set of clusters. Let's notice something interesting about this set C, which is that it's a tree. What do I mean by a tree? What I mean is it has a tree-like structure, which is that if I take any 2 sets in here, one of the following is true. Either A is contained in B, or B is contained in A, or they're disjoint. So for example, here's a set A, here's a set B, and you can see that those 2 are nested in each other. On the other hand, this set over here, it's disjoint from this, and so on. So it has a tree-like structure, perhaps I should say, because that's how a tree behaves. Everything the tree splits, everything has an ancestor. At one point is either above another point in the tree or is disjoint. So you can think of this collection of level sets has this nice structure, this tree-like structure. And in fact, we could draw a tree. I'm just going to draw a picture of it. Here it is. That is the tree that represents that density, or is a tree that represents that density. All what I mean by this tree is I'm saying that there's a mode here, and then there's a collection of level sets. There's a mode here, there's a collection of level sets, and then at some point, those level sets merge, which is what happens here. The cool thing about this is I can do this independently of dimension. you can, because this tree structure always exists, I can take a density of any dimension and always draw it as a tree. Now there's a certain amount of arbitrariness here, because in one dimension you can see how this lines up. In 10 dimensions, what does it mean if I draw a tree that looks like this? Well, it's telling me that as I go up the density, the level sets split, then the level sets split again, and level sets, but the idea of left or right doesn't make sense. So in other words, how I drew this, the vertical part makes sense, but how I drew it horizontally, like whether I put the split here or put the split here, is completely arbitrary. Okay, in other words, if I were to put, another way to say this is if I put data points on here, I could put actually a data point here, 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 here. This tree would correctly show me in the density level sets which level sets are nested in which other level sets. Like this data point is in this level set, but it's nested within this one, but then it splits over here and so on. It correctly shows the topological structure of the tree, in other words. But you can't say that this split is to the left of this split, because we could be talking about something in high dimensions.
These elements in the set C, these are also themselves are sets that contains C1 to CKT, right? So how do you say that A is contained in B? Because these small sets are different.
No, I'm just saying that if I take one, I'm going to take, here's A. That's A set in there, right?
Shouldn't A be these two sets?
No, it's not the level sets. It's the connected components of the level sets. It's these.
But that big C is a collection of...
Big C is only the connected components of the level set, not the level set itself.
Oh.
Yeah, it's like a bag of sets.
If you apply this to the ring, then how would you find?
So what's going to happen with the ring, I'm going to show you some examples in a minute, but what will happen in the ring is there will be maybe a mode here and a mode here, but they won't last long. So what's going to happen maybe is something like this. This is a little bit fake, but it's probably going to look something like this. There might be a little mode here, probably they won't be exactly even, but they'll merge very quickly into one component.
So they won't merge at the same time?
Yeah, I made it look like they're going to merge exactly at the same time, which is a bit of a fantasy, but it's easier to draw. So you can see there's a lot more shape information here. And let me tell you how we actually compute this thing. Well, first of all, the real way to compute it is to use existing software. Because I have to tell you that it's not that hard to program, but it does involve recursion. I don't know about you, but anytime I have to do something recursively and keep track of tree structures, I find that painful. So there are lots of programs that will do this for you. So I'll mention that, actually there's three. I only put two here. Let me tell you the three that I know about. Is there any Python fans here? I thought you computer scientists love Python. There's this thing on, I have the link here. It's called Debacle. So it's density-based clustering. And it's in Python. It runs very fast. The link is right there. And it's continually under development. We have our own package at CMU called TDA, Topological Data Analysis. And there's a function in there you'll see. This is R code, though. And it runs, you just give it the data, it gives you the tree, the density tree. And then there's another one in R, I just remembered, called DenPro. I'm not sure what that even stands for, but these are in R. This is Python. I'm sure somebody has written one in MATLAB, but since I'm not a MATLAB user, I can't tell you the name of it. But let me show you the kind of things that come out, and then I'll tell you how they're actually computed, because I haven't given you the details yet. But like here's a simple data set, and you can see there's kind of two clusters that are, it's not clear whether they should be called two clusters or one cluster, then a third cluster, and to the left of that is the corresponding tree. And so you can see that there's these two clusters here. They merge very soon. They have a short lifetime, as we say. And then there's this bigger cluster over here, and eventually when I come down low enough, it all just gets merged into one cluster. And here's a three-dimensional version of exactly the same thing. So this is what comes out of the program. You just pump into the program the data, and out's going to come this tree, which will show you the clustering structure. The nice thing about this is it gives you the whole clustering structure. And you can see a lot more doing this, perhaps, than just finding the modes. On the other hand, if you decide you want definite clusters, if you don't want to look at the structure, you just want to say, look, I just want a set of clusters, then the mode clustering just gives you out a set of clusters. So it really depends on which one which kind of output you want to get. But what I haven't told you is how do these programs figure out the connected components? Because that's actually a non-trivial problem. The density estimation part is going to be clear. So L of t looks like this. Well, not surprisingly, the estimate looks like this. You just insert density estimator. That's fine. How do I actually compute the connected components of this set? If I tell you, let's just do it in 2 dimensions. If I tell you I have a 2-dimensional kernel density estimator, and I give you t, so I tell you to cut it here, how do I know where the connected components are? That's actually not obvious how to do that. So the most common way of doing that is, first of all, to find the set of all data points where the density is bigger than t. So now what I'm going to get is a set of points. And the way I've drawn it, it might look obvious how to get the connected components, but it might not be that simple. What people usually do at this point is, let me see if I expressed it as a graph or a union. What you do now is you form a graph. So what you do is you take all these points, these are only the points satisfying this condition, and now any 2 points in this set that are less than or equal to some threshold epsilon, you connect them. So I'm going to connect this point, this point, this point, this point, this point. Now I have a graph, and now there are algorithms like breadth first search algorithms that, given a graph, you say find the connected components, and it can find the connected components pretty quickly. That's what this program is doing. And I think I said h in here, but actually, how do you choose this epsilon? I usually take it to be 2 times the bandwidth. I don't have any justification except that that seems to work pretty good. This is not a statistical thing, right? This is a numerical thing. In principle, you should be able to figure out which sets are in a connected component. If you could evaluate for any 2 points, if you could check every possible path between those 2 points to say, does the density ever dip below t? You could say, yes, they're in the same component or not, but that's not computationally feasible. So this is a computational issue, is how to discover the connected components. And this is pretty much what everybody does, is you just make a graph. I usually use 2 times the bandwidth. Again, I don't have any theory for that, but it just seems to work well. And this is what's going on in all of those programs, some version of this. Not every program is doing it the same. I should say Debacle, for example, is not using a kernel estimator. It's using something called a k-nearest neighbor density estimator, which I don't remember if we talked about it or not, but it's just another density estimator. And so you can use different density estimators, and you can use different rules for finding the connected components, but morally they're all the same thing. We're just finding all the points above the threshold and then forming a graph and finding the connected components. Now, when I lower the threshold t, you could redo the whole calculation. Find all the points bigger than t, find the connected components, to get the level set. But you can see that would be very inefficient, right? Somehow it seems like if you keep track of what you did at the last step, you should be able to do this more efficiently. That's why it's kind of a pain to program this properly. But if you program it properly, it's much faster than just doing some sort of simple brute force thing, which is why I use their programs and I don't try to program it myself. But it's pretty simple. We just find the set, find the connected components. And then drawing the tree is also, it's just a lot of bookkeeping. You have to keep track of these level sets, and when they merge, when 2 level sets merge, if I keep adding points, if I keep dropping the level, I'm going to keep adding points, and eventually these two will merge. So I have to draw a horizontal line somewhere there, and you have to make some sort of graphical choice about where to put that and so on. So there's just a lot of bookkeeping to do.
Wait, so why do they actually have to merge as far as the connected components go?
That's what you're trying to keep track of, is when do the connected components merge.
But I mean, we have some fixed distance, right, that we need them to points to be within. So they
Right.
have to be in the level set, right? And they have to be within some distance from one another. But I mean, there's no saying that our data actually have to be connected in that way, right? I can have two, a bimodal distribution where the two clusters.
Oh, they might not merge. No, they might not merge, but you're trying to find out if they merge and where.
Okay.
Right? I mean, just think again. Think of a density that looks like this. So, these will eventually merge. This and this will never merge.
So for ring situation, I'm still thinking about the ring. So
Oh, the ring.
yeah.
Yes.
Yes. So they merge at different times, but they can be thought of as one level, meaning that
Right.
that there is
So
a-
let's draw what it really is going to look like. It's probably going to look like this.
Yeah. So that means there is a parameter that actually says if it is within this bounds, then they must be grouped into one.
Well, so you're getting ahead of me, which is, can I now tell you which of these are significant or not? Right? You could say none of these modes are significant. Maybe I should group them together. There is a way to do that, which will solve this problem. I think it might be what's coming up shortly. I'm not sure. I'll probably get to this on Thursday. Yeah. So we can. I think the question is really, these little leaves here look insignificant in some statistical sense. Maybe we should just. That's telling us we really should just. Well, I guess it would just look like one. Not a very interesting tree, but a single tree. And yes, there's a way of dealing with that, which probably get to on Thursday.
What it means that to take if epsilon equals to h, if I take another epsilon, what should happen?
Well, the question is, why did I take epsilon equal to h or 2h? There actually is some theory about how large you should choose epsilon so you actually recover the correct connected components. And it does tell us that epsilon should be something like, I think, of order h. But we need to make a practical choice. And the only reason why I'm saying to use 2h is this is just my experience that seems to work well. I don't have any theory that tells you that's the best thing to do.
So, I mean, we have these two very different ways of clustering. I'm just curious what the kind of applications are that we would be interested in clustering in either case.
I think you can apply this to any clustering problem. Anytime you're clustering, I mean, there's a fundamental question, which is when do we want to cluster, right? But I think anytime you're clustering, these are viable methods.
Yeah, so, I mean, I guess maybe I'm just not familiar with the applications of clustering in general. So.
Oh, yeah. So there's lots and lots of examples of clustering. I mean, it's more of an exploratory tool. So a good example would be, like a more, say, modern example is you have a few hundred people and you've measured 5,000 genes on them, and you want to group the people together. See, are there groups of similar people, and you want to group them based on their genes. So, for example, here's an interesting success story I'll tell you for debacle. So debacle was written by Brian Kent, who actually he was a PhD student here quite a while ago. And here is the clustering one. He was motivated by a problem in neuroscience, which is why he actually created the program. But he applied it to a different problem, which I found very fascinating. He took a bunch of people, a few hundred people, and on each person there had been measured, I'm going to say 20,000 SNPs. You know what a SNP is? A single nucleotide polymorphism, like a single spot on your genome. Okay. So you have, say, n equals to, I'm going to say 200, but the dimension was like 20,000. And he ran this. And I said to Brian, you can't do density estimation in 20,000 dimensions. You're not going to find clusters there. Well, he found clusters. And I said, yeah, but how do you know they're meaningful? Well, he went to one of my colleagues who happens to be a geneticist. And she was able to look at the geographic region from which these people were collected. And sure enough, these clusters corresponded exactly to Asia, North America. It reproduced the geography perfectly. And then the higher order clusters, higher in the tree, corresponded pretty closely to sub-geographic regions within the in the data set. So that's the kind of thing you're doing. You're looking for structure. And in this case, it happened to be we could check the structure, against something known. But generally, in clustering, that's what we're doing. We're looking for structure, and then you're going to say, okay, is this structure interesting? Is it useful?
So, I guess maybe that problem actually illustrates part of what's confusing me here. So it seems like we have some kind of similarity metric, right, on data points. And it seems like that itself ought to carry the information about geographically, right?
Well, we don't pretend we don't have the geography, though.
Well, but that's the idea, right? So if there is that information in the gene data, right? Why would we cluster it before we just looked at sort of the
SNPs?
relationships between the samples, right?
How do you look at 20,000 SNPs? On each person, I have 20,000. How do I say who's similar and how similar are they? See, it's not so obvious. Think about when I draw a two-dimensional picture, it's pretty obvious. This is something going on here and there's something going on here. But when you're in 20,000 dimensions, it's not so obvious how to say what the groups are in the data. We're just looking for groups in the data. And beyond 1 or 2 dimensions, it's just, if you don't have a well-defined method for doing it, it's just not obvious how to do it.
When you are seeing H here, does it mean that we are using the kernels of the Gaussian kernel or just any kernel?
Well, I always use the Gaussian kernel. But yeah, this is a very, let me put quotes around this. Don't say that this is like the official thing to use, because this is just my advice. These programs that I've mentioned, they have defaults built in. I don't know if whatever they use, but they're just defaults based on their guys who wrote it, their experience, and what seemed to work well. Yeah, sorry, I didn't kind of give an overview of clustering. I just kind of assumed everybody was familiar with clustering and so on. But clustering, you're just trying to find groups in the data, and the reason could be for many, many, many different reasons. But it's more of an exploratory tool for exploring data. Sometimes it's used formally, like in something called semi-supervised learning, which we didn't talk about, at least not in any detail, where you need the clusters explicitly to do some of the algorithms. Okay, so so here's what we'll do next. I want to talk a little bit about, we'll do this on Thursday, I guess, just a little bit about the theory that's available for this. And then I want to talk about something, a little bit of modern topological data analysis, just a little bit, of something called persistence, which is just a way to tell you which clusters are significant clusters or not significant clusters. Okay, then I'm going to start talking about more traditional methods like k-means clustering, hierarchical clustering, spectral clustering, and we'll try to see what the relationship is between all of these different things. Any questions?
So out of curiosity, maybe this is where persistence is going, but could you do something like bootstrapping and see sort of the variability of
We are going to use the bootstrap, in fact, yeah. By the way, I forgot to say one other thing at the beginning of the class. You'll notice that there's a bunch of topics for the rest of the course. Okay, those I threw in as placeholders. I just threw something in there. I'm not necessarily going to cover those topics. We're definitely going to do clustering and do graphical models. Then at that point, I have to decide what to cover. And so if you have ideas, if you have suggestions or requests, let me know. We have a lot of flexibility about what we could do, well, up to things that I'm able to tell you about. There are a few restrictions on the degrees of freedom there. So don't take the list of topics there too seriously, right? Those are placeholders. And if you have requests, let me know and I'll consider them. All right, so I'll see you on Thursday.